Here we have a short page of notes looking at dielectrics. Now, we're going to look at two very famous and important experiments done by Michael Faraday on our next page of notes, so we need to remind ourselves about what dielectric materials do and the properties of these materials. Now, any non-conducting material placed between the plates of the capacitor we refer to as the dielectric. So it's an insulating material, and we will see that the property of these insulating materials that we most want to focus on is the polarization or partial polarization that will reduce the net electric field between the plates when that material, the dielectric material, is placed between them. So the dielectric constant we've talked about before, but to remind you, is a value kappa given by the electric field in vacuum. That would be prior to having a dielectric between the plates. So if we have our parallel plate capacitor here, I'm going to, in black, let that represent the vacuum electric fields. That's our E sub vacuum. The dielectric material will polarize, generating its own electric field such that the net electric field is going to equal the original vacuum electric field minus the electric field with the material in place. So it's that, and we'll see from Faraday's experiments on our next page, it's that polarization, that reduction in the electric field that allows for the capacitance to always be greater when you insert a dielectric material between the plates. So the smaller the electric field between the plates, so the greater the polarization we get, the smaller the electric field between the plates, the greater the kappa value. So our dielectric constant, a large dielectric constant, means there's a lot of polarization going on between the plates, reducing the electric field between the plates, making a large kappa value. And again, we'll see on our next page of notes how that results in a larger capacitance. So dielectric constant we have talked about. That's what I have here on the left-hand side of the page. I have some typical values for dielectric materials: wood, silicon, H2O, and strontium titanate. Strontium titanate was the largest I could find, but you are certainly welcome to do a web search to see if you can find larger ones. And again, last time, we are focusing on the fact that the bigger the kappa value means the greater the polarization. It's reducing that net electric field between the plates. And let me just jump right back up here real quick just to emphasize, as we've seen before, that the kappa is 1 for vacuum, because if the material between the plates is vacuum itself, of course you get electric field on vacuum divided by electric field on vacuum equals 1. Now, the last thing we need to do here is distinguish between dielectric constant and dielectric strength. Dielectric strength refers to a totally different concept. Dielectric strength is electric field. So it's the electric field value in volts per meter that allows for electrical breakdown, meaning lightning. So the electrons are flowing through the gap, through that material, and for air, that happens at roughly an electric field value of 3,000 volts per millimeter. So in the wintertime, when you get that spark between your finger and the doorknob, or any type of that electrostatic shock spark, you have roughly 3,000 volts per millimeter traveling across that distance. Now for paper, it's 16,000, breakdown voltage 16,000 volts per millimeter, glass is 14,000, and strontium titanate is 8,000 volts per millimeter. So notice the two don't necessarily correspond in terms of getting bigger and getting bigger. That's why I wanted to make sure I had the distinction here between the two, so that you would be aware of the language and what it means when they talk about dielectric strength versus the dielectric constant. So pause the video, get your annotations down, and we can, of course, discuss this, and we will go on to look at Faraday's experiments.